Hi, welcome to Unit 7, Day 5. This is Example 3. Just like with all the previous examples 1 and 2, I will be showing you the work for this using the step-by-step method first and then the one-line method, but I'll let you know what part of the video will start. So whichever method that you're following, make sure that you're watching that correct part. So we're going to start with the step-by-step method. All right, so in this problem, they're saying that we have 0.827 grams of NaCl and 1.305 grams of AgNO3, so sodium chloride and silver nitrate are our reactants. They want to know what's the limiting reactant, so which one is going to run out first or produce the least amount of product. And they also want us to determine the maximum amount of AgCl, our product, one of our products. So that will be our theoretical yield. And then they're telling us if we isolated 0.7 grams, what's the percent yield? So we got to do all of this, all right? Okay, so first step is to balance our chemical equation. So we're going to take a look at this reaction. This is a double displacement reaction. I know it's a double displacement reaction because I have 2 compounds in my reactant and 2 compounds on my product side. And I notice that it's just a switching of partners, right? So sodium goes with nitrate, silver goes with chloride to form the 2 partners. All right, so for double displacement reactions, instead of breaking everything down into elements, what we like to do is we like to break them down by groups. So the metal, or the cation, I should say, we'll list those for each one. So the cation and anion of each one. So something like NO3, we don't break it down to nitrogen and oxygen separately. We keep it together as a polyatomic anion. It just makes our life easier. All right, so we've got 1 sodium, 1 chlorine, 1 silver, 1 nitrate group, one sodium, 1 chlorine, 1 silver, and then 1 nitrate group. So this is actually already balanced, so all the coefficients are invisible ones. I'll just write them in. All right, cool. All right, next step is to calculate the amount of each product each reactant can make. So we're going to figure out the amount of product we can make from NaCl and AgNO3 separately. Now, before we do that, what's the product that we should be focusing on? Because there's 2 here. Well, it tells us to determine the maximum amount of AgCl, so that's the product we have to focus on. Whatever product that they're giving us that we need for our theoretical yield, that's the product that you're focusing on. So we're going to focus on this one. Okay, so my work here is to go from grams of NaCl to grams of AgCl. And I also have to do that for the other reactants, AgNO3. So grams of AgNO3 to grams of the product AgCl. Okay. All right, so first step, we're going to convert from grams of NaCl to moles of NaCl. So we're doing this first step here. Boop, boop. All right, so 0.827 grams of NaCl over 1. Now, to do the conversion, I need to use my periodic table to get the molar mass. So for NaCl, it will be 22.99 plus 35.45. I've actually already calculated that. So 1 mole of NaCl is equal to 58.44 grams. Okay, so that means that the 1 mole on top. And the 58.44 grams on the bottom, so that the grams of NaCl can cancel out. And that gives me 0.0142 moles of NaCl. Okay. Now we need to go from our moles of given to moles of find. We're trying to find AgCl here. So we take what we got in the previous step. Now to do this step, we use the coefficients in the balanced chemical equation. It's a 1-to-1 mole ratio, which actually makes our work so much easier. So 1 mole of AgCl and then 1 mole of NaCl. That means we don't even need to do the math. So whenever it's a 1-to-1 mole ratio, the moles will be the same. So the moles of NaCl will be equivalent to the moles of AgCl. So we have 0.0142 moles AgCl. All right. Last step for this side is to go from moles of AgCl to grams of AgCl. And for that, we need the molar mass, which I have also already calculated using the periodic table. It is 143.22 grams. So we have 0.0142 moles AgCl over 1 times, I'll put the 1 mole AgCl on the bottom and the 143.22 grams on top, so the moles of AgCl cancel out and I get my grams. Okay, cool. So that number times 143.22 and I get 2.03 because I'm using 3 sig figs here. So I'm going to write that up here so it's easier to see. Okay. All right. Now we're going to do that for the second one. Same process, except for different reactants. So we're going to go from grams of AgNO3 to moles of AgNO3. That's our other reactant, AgNO3. All right, we're given 1.305 grams of AgNO3. All right, so we need to find the molar mass of AgNO3, which I have done as well, using that periodic table. So we get it to be 169.88. Okay, so 169.88 grams of AgNO3 goes on the bottom, so the grams of AgNO3 cancel out, and then the 1 mole of AgNO3 goes on top. Whoosh, whoosh. Okay, so we've got here 0.00768 2 moles of AgNO3 of silver nitrate. Okay, so we got our, we're going to go now from moles of silver nitrate to moles of silver chloride. So for that, we use the coefficients in the balanced chemical equation. Once again, this one is pretty easy because everything's 1-to-1, which is nice. Makes our work so much easier. Okay, so then that means we have the same number. Okay, so now that we've done that, we are now going to go from moles of, oops, let's just say AgCl. Moles of AgCl to grams of AgCl. So we have 0.00762 grams moles of AgCl. And then I'll use my molar mass of AgCl to get the mass of that. So 1 mole AgCl goes on the bottom, and then 43.22 grams go on top. We get 1.10. Okay. So that means that for this process, it gives us 1.10, okay, grams of AgCl. All right, so what's our limiting, what's our theoretical? All right, we find the one that gives us the least amount. The AgNO3 gives us the least amount of product. So that means that limiting reactant is AgNO3 because it gives the least amount of product, and the theoretical yield is 1.10 grams of AgCl. Now, in terms of percent yield, it is going to be whatever the actual yield is. So they tell us that we isolated 0.7, so that's what we actually got. And divided by our theoretical yield, which is 1.10 grams times 100. .6%. Okay. Not the greatest yield, but hey, there you go. All right, so that's it for the step-by-step method. The next part of this video will show you the one-line method for solving. Okay, so if you're watching this part of the video, you're doing the one-line method, and the process is to go from the mass of each reactant to the mass of the product. Now, in this example, there are two products here, but since they're telling us to determine the maximum amount or theoretical yield of AgCl, that's the product that we're focusing on. So we don't worry about this sodium nitrate, the NaNO3, we're focusing on this one because that's what we're trying to find the theoretical yield of. All right, so we go from grams of NaCl to, we're trying to get to grams of AgCl. And to do that, we would start with the mass of NaCl that they give us, 0.827 grams over 1. Second fraction comes from the molar mass. So the molar mass of NaCl is 58.44 grams. So that goes on the bottom so that the grams cancel out. And then 1 mole goes on the top. Remember, for molar mass, it's always set equivalent to 1 mole. So I got this number from the periodic table. I'm going to set that equal always to 1 mole. All right, second part is to go from our moles of given to moles of fine using the coefficients and balanced chemical equation. These coefficients are all 1, so that's pretty cool. So that would be 1 mole of NaCl and 1 mole of AgCl. And then the last part is to go from the moles of our fine to the mass of our fine using the molar mass of silver chloride, AgCl, and the molar mass of silver chloride is 143.22 grams. I found that before. So I want to get rid of moles of AgCl, so that goes on the bottom, and then the mass would go on the top. So to do my math, I multiply 0.827 times 143.22 and then divide that value by 58.44. And when I do that in my calculator, I get 2.03 grams of AgCl. So that means that the 0.827 grams of NaCl will give me 2.03 grams of AgCl. All right, we're going to try that now for the, I'll just do it here, grams of silver nitrate to grams of AgCl. Okay. All right, so just use a little bit of paper here. And looks like I'm running out of room. Okay, so for this part, we are starting with 1.305 grams of AgNO3. Which I get from my problem, right? So I put that over 1. I now want to convert that to moles of AgNO3 using the molar mass of AgNO3, which I have already determined is 169.88 using the periodic table. So 169.88 grams of AgNO3 over 1 mole of AgNO3. All right, so now I have the moles of given. Now I need to go from moles of given to moles of fine. For that, use the coefficients in the balanced chemical equation. As I said, all the coefficients are 1, so that's super easy. 1 mole of AgNO3. And then 1 mole of AgCl. And then the last part is to convert from moles of the fine to the mass of fine using the molar mass. So 143.22 grams of AgCl over 1 mole of AgCl. And then all right, so then I just multiply 1.305 times 143.22 and then divide it by 169.88. And when I do that, I get 1.09 grams. Okay, oops, sorry. 1.09 grams. All right, so which one is my limiting reactant and theoretical yield? It's the one that gives me the smallest number, and so that's AgNO3 is my limiting reactant because it gives the least amount. And the amount of AgCl I get is, here when I calculated, when I did it all in one line, I actually got 1.09, but with doing the step-by-step method, I got 1.10, but that's fine because it has to do with sig figs. Remember, the last digit will be, can be slightly off, depending on how you round things. So, so here I put 1.10, but you can put 1.09 if that's what you got. And that's my theoretical yield of AgCl. Finally, for the percent yield, I went to the top of my problem, and it tells me that I isolated 0.700 gram. This is my actual yield, so I put that, according to the equation, I put that on the top, and then the theoretical on the bottom, multiplied by 100, it gets 63.6%. Okay, that is it for example 3. Have a quality day.